Just as a reminder, last time we were talking about critical exponents for percolation. I've written them all up on the board here again, just so you can help remember, just to remind you rather of the notational conventions for the different exponents. Last time we were talking about the scaling and hyperscaling relations, which we described as these, for now, non-rigorous relationships between the different exponents. And we talked about the conjectures for what these exponents should be for nearest neighbor percolation. So today I want to start talking about long-range percolation. And this is a variant on the model, which is interesting for various reasons. And one of them that I want to tell you about over the course of this week is that we can actually prove many things about long-range percolation that seem currently out of reach for nearest neighbor models. So let me start by defining weighted graphs. So a weighted graph will be a triple, well, as usual in a graph, we'll have a vertex set and an edge set. We'll also have a weight function j, where j is a non-negative assignment of weights to vertices. And Bernoulli percolation on a weighted graph. So we're now going to write beta for the parameter rather than p. So E is open with probability 1 minus e to the minus beta j of e. Okay? So where beta is a non-negative parameter. Okay? So you should think beta is the analog of p, right? If I took j to just be the constant function 1, then this is equivalent to normal to ordinary percolation, but with p is 1 minus e to the minus beta. Okay? And in fact, even for ordinary percolation, this is often a very convenient parameterization to work with. It makes the for example, Rousseau's formula, things like that come out rather more cleanly than it does in the normal parameterization. Okay. Good. So we can define transitive weighted graphs like we normally would. So transitive means for all vertices x, y, there exists a symmetry, an automorphism of the graph mapping x to y, where an automorphism of a weighted graph is defined in the obvious way. So it has to be a graph automorphism, it has to preserve the weights. Okay? And we'll always assume that if I look at any fixed vertex and I sum over E incident to V, that this is finite. So in other words, the total weight of all edges emanating from a given vertex is finite. In the case that this is transitive, of course, these quantities are all the same, and I'll write them as j. Okay? And of course, this means if I do this, then the expected number of the expected degree of each vertex is finite when I do percolation. Okay? So regarding this specific function, this is not terribly important. This is just one algebraically convenient way of getting a number between 0 and 1, which is roughly beta times j when it's small. Okay? Now this particular choice of the 1 minus the exponential corresponds exactly to taking a Poisson process of edges with intensity beta times j, and then just defining an edge to be open if there's at least one edge there in the Poisson process. Okay. So long range So if J is a function on ZD, which is symmetric, i.e. J of x is equal to J of negative x, and integrable, which means that the sum is finite, then we can define a weighted graph whose vertex set is ZD, whose edges are are all possible edges, and whose weight is given by J. The weight of the edge between x and y is just equal to J of x minus y. Okay, so as we continue, I won't really distinguish between this kernel J being a function of two variables or this kernel being a function of a single variable. Of course, these are equivalent, except later on in the course of some of the proofs, we'll actually want to consider non-translation invariant kernels, and then, of course, we'll want to use this notation with 2 points. Okay. So the particular kernel that we're going to be most interested in. So of course, for one thing, you could just take J to be the indicator that x and y are adjacent in the hypercubic grid, and then studying percolation with that kernel is just completely equivalent to studying nearest neighbor percolation. What we're going to be interested in is to take J to be a power of the distance, and it's going to be convenient to write this power in this form as minus d minus alpha, where alpha is positive. Okay, and I'll allow this to be any norm. If I want to specify the Euclidean norm at some stages, I'll use the subscript 2. Okay, so this alpha being positive, this ensures integrability. Okay, that's a simple calculus exercise you can check. Okay, so just as a warning, within the long-range percolation literature, there are a few different notational conventions one sees for this power. So sometimes what I've written as d plus alpha is just written as alpha. It's often d plus alpha is called s as well. So I'll be talking a lot about the regime like alpha between 0 and d. You'll often see s between d and 2d, and if you read other papers, and that's exactly equivalent to this. Okay. The reason that I prefer this notation with the minus d minus alpha is that for those of you who know about this, and we'll talk about it more later, this alpha is precisely the same as the standard alpha in the definition of an alpha stable random variable, alpha stable Levy process, and so on. Okay. Good. Okay. So the basic idea is that varying alpha. So again, you should think that when we study this model, we're going to fix this parameter alpha, a bit like how we fix the dimension ordinarily. I mean, we're still fixing the dimension now, of course, as well. And then we vary beta to induce a phase transition. So one of the key observations about long-range models in general, and in particular for long-range percolation, is that varying this parameter alpha is at least somewhat analogous to varying the dimension. Okay. And one of the nice things about this that you can take as a motivation for studying long-range models is that, previously we were talking about how in physics they often like to do expansions in the dimension, where you take d is 6 minus epsilon. And one of the nice things here is alpha is, of course, a parameter we are absolutely entitled to vary continuously. And so this is not something that has been done yet, although it's a natural next thing to do after the work that I'm telling you about, that we can make sense of these things about epsilon expansions. In fact, that has been done by Gordon Slade for the spin-ON model. Okay, so one way you can understand this to a coarse level, this is good as a rule of thumb. It has some limitations, as I'll say soon, is via what's called the effective dimension, which is defined to be the maximum of d and 2d over alpha. Okay, so you shouldn't rely too strongly on this notion. It's not really the case that knowing the effective dimension tells you everything, particularly in the low dimensional regime. It's not like models with the same effective dimension have the same exponents. It does give us the correct answer for what happens in high dimensions. So we'll see that if the effective dimension is strictly larger than 6, then you do indeed get mean field behavior.
So in that you were saying you hope that for expanding or to recover below 6 as epsilon expansion, with this formula would still hold, or you'd have to change the dimension?
Yeah, that's a good question. There might be some scaling you have to do. I need to think about that. There are some interesting things with this possible limitations to this whole approach of doing the expansions, in that I'll say something about this later, but some of the exponents I can prove, subject to the validity of some natural conjectures, that they cannot be analytic functions of alpha on this intermediate dimensional regime. So, if the functions are not always analytic, then these expansions are maybe anyway, there's some subtleties going on there.
So how do you prove the 2D over alpha?
How do I prove it? Well, for here it's just a formula. But if you want an interpretation of this, if you take the random walk with transition kernel proportional to this kernel J, the symbol just means there's some constant, so that this is equal to this times a constant. Okay, then if you look at the n-step return probabilities to the origin, it decays like n to the minus df over 2. So in particular, this effective dimension, you can think of it as being what's called the spectral dimension of the random walk, which just means that it's the value you can put here that makes this true. Okay. Good. So okay. So that's the model, and of course, there's many interesting things we can ask about it. In particular, we can ask all the same questions that we already asked about the nearest neighbor model. Okay, and one of the surprising things, if you're new to this business, is that you might think, well, we took our nice familiar nearest neighbor model, and then we sort of added some bells and whistles, and we made it more complicated. So the surprising thing is that we can actually prove a lot more about this model than we can prove about the nearest neighbor model, at least in some regimes of alpha. Okay, and it tends to be, the smaller alpha is, the more heavy-tailed the model is, and these additional tools that we have available to us in the long-range setting become more and more powerful. Okay. Now, of course, if alpha is really small, then by this formula, the effective dimension will be very large, and then you can think, well, we just know how to analyze high-dimensional things. And that's true, and all those techniques do carry over to this regime. So the more interesting thing, perhaps, is that even in the regime where you're not high effective dimensional, there's quite a lot we can prove. Okay, so let me start by defining the critical parameter like we did before. So beta c, just exactly like we defined PC, will be the infemal value of beta such that infinite clusters exist almost surely. And again, you could say with positive probability instead of almost surely, and you get an equivalent definition. Okay. And, previously we saw that if you have max degree d, then PC is at least 1 over d minus 1. And you get a very similar bound here, which is that beta c is always at least 1 over the sum of the weights around the origin, which is positive. Okay? By the same proof. Okay? And regarding when beta c is finite, which is the analog of PC being less than 1, beta c is less than infinity if and only if d is at least 2 or d equals 1 and alpha is less than or equal to 1. Okay? So in particular, once you start considering long-range models, you can now have phase transitions in one dimension. Of course, that shouldn't be surprising from this effective dimension formula, right? Because if I make alpha small, even if d is 1, it's like making the effective dimension large. Okay. So the case d at least 2, this just follows from the theorem we had about PC being less than 1 on ZD, right? Because, we've set things up so that j of each of the nearest neighbors is positive. So you can think that this weighted graph contains a copy of ZD as a subgraph, maybe with the weight scaled by a constant. Okay, so just the fact that basically you get a comparison between the nearest neighbor model and the long-range model, which ensures that beta c is finite when d is at least 2. The case when d is 1, of course, doesn't follow from the comparison with the nearest neighbor model. And it's a harder theorem to prove, particularly in the case alpha equals 1, which is quite subtle. And I believe that this result is essentially due to Freeman-Dyson back in the 60s, who proved the same result for the Ising model. But again, as I've said, the Ising model results for just whether the phase transition is non-trivial or not, it's equivalent for percolation in the Ising model. Okay, so we'll actually see a proof of this apart from in the alpha equals 1 case over the course of this lecture series. In fact, we won't really prove this directly. We'll just prove that there's no infinite clusters at beta c, and that will just imply that beta c is finite because, of course, at beta c equals infinity, you do have no infinite clusters. Okay. So, as I said, this model is in some senses surprisingly easier to understand than the nearest neighbor model. And I think a very nice example of this is a result of Noemberger from 2002, which is that if alpha is strictly less than d, then there are no infinite clusters at beta c. Okay, so of course this is something we would very much like to be able to prove for the nearest neighbor models. And for the long-range models, we can really prove it, at least when alpha is not too large. Of course, as alpha gets larger, you get more and more similar to the nearest neighbor model. But I want to stress that this cutoff of d is actually quite large, particularly in dimension 3 or something, and it's going to be well separated from much larger than the regime where you actually start behaving like the nearest neighbor model. So for alpha close to 3, for example, in 3 dimensions, we expect actually this model to already be behaving essentially exactly like the nearest neighbor model at large scales, but these proof techniques still let us prove continuity of the phase transition for it. Okay. Good. Now, of course, the conjecture is that if d is at least 2, there are no infinite clusters at beta c. Okay, but this remains open in the case when alpha is large, and again, the model becomes more and more similar to the nearest neighbor model as alpha gets larger. On the other hand, it's a theorem of Eisenman and Newman from the 80s that this is not true for d equals alpha equals 1. So when d equals alpha equals 1, beta c is finite, but you actually already have an infinite cluster at the critical point. So this is what we call a discontinuous phase transition. Okay, and you can see, it's something interesting where this point is right on the boundary of when you have a phase transition at all, and at this boundary point you actually have a discontinuous phase transition.
So a priori, there we are in a regime very far from your effective dimension being larger than 6. So there can be a lot of...
Yeah, this is like a very low dimensional regime. I guess one way you can think of this is that this is something about the model at the lower critical dimension, which is the dimension at which you begin to have a phase transition at all. And it's saying for this particular model, at the lower critical dimension in this way, you actually do get a phase transition, but it's a discontinuous phase transition. So this is really the totally opposite end of the spectrum from the high dimensional stuff. And as we'll see, if you're in one dimension but alpha is just very close to 1, then you'll have a continuous phase transition, no infinite clusters at criticality, but the exponents will be very large, diverging as you approach alpha equals 1. Okay. So as I said, we're going to want to understand all the same questions about the long-range model as we wanted to understand about the short-range model, namely critical exponents, scaling limits, and so on. Now, on the other hand, when you study the long-range model, there are also additional questions that appear that you can't, that don't make sense for the nearest neighbor model, which is, well, when is the model really long range? Okay, by which I mean, if alpha is very large, well, you have this power law decay of the edge kernel, but it could be a very light power law decay. And maybe once alpha gets large enough, you should just start behaving the same as the nearest neighbor model at large scales, and the critical exponent should be the same, scaling limits the same, and so on. Okay. So to get some feeling for this question, it's good to think about the analogous question for random walk, which is very classical. Okay, so again, we'll consider the random walk with this kernel. Okay. Now, if you and let's start the random walk at the origin. If you look at the pth moments for how far the random walk goes in a single step, well, you can compute what this is. Again, up to constants, we can just sum over the boundaries of boxes. In each boundary of the box, there's r to the d minus 1 points. Each one of them I jump to with probability of this order. And if I get there, I win an r to the p, right? So, okay, so these two d's cancel. So I get the sum of r to the minus alpha plus p minus 1. And this is finite if and only if p is strictly less than alpha. Okay, so you can think, again, this is one reason why I think this particular parameterization in terms of alpha is nice. Alpha is just the number of moments that you have if you follow one step of the associated random walk. Okay. Now, in particular, if alpha is bigger than 2, you get finite variance, or finite second moments. Okay. By the way, because J is symmetric, this transition matrix is also symmetric, so the walk does not have drift. Okay. And of course, if you have a finite variance random walk, it's a very classical result of probability, Donska's invariance theorem, and of course it's related to the central limit theorem, that the walk converges to Brownian motion. So if I take the walk at time lambda t, where lambda is a large constant, and I round because the walk's only defined integers, and I think of this as a process in continuous time, then it converges as the scaling factor lambda goes to infinity to Brownian motion. Okay? If you like, you can think of this as the definition of what Brownian motion is. It's just the continuum limit of the simple random walk. Okay? In particular, this is a random continuous function. Okay. Okay, so probably this is familiar to many of you. Okay, and part of, the point of the central limit theorem and of Donska's invariance principle, which just means the convergence to Brownian motion, is that Brownian motion is a universal limit object. It doesn't matter which random walk you take, provided it has finite variance, then you will get this Brownian motion in the limit. Now, strictly speaking, you should rescale by some constant involving the variance if you want to get the standard Brownian motion. But here we're getting Brownian motion with some potentially non-integer variance. Okay, and of course you can also characterize Brownian motion intrinsically. It's the process with it's a random continuous function. It has independent Gaussian increments, and so on. Okay. Good. Now, what about if alpha is less than 2? So here we have infinite variance. And in this case, again, it's very classical that we have a limit process, but it's no longer a Brownian motion, it's a Levy process. Okay? So in particular, the scaling we have to do is different. We have to rescale by a factor of lambda to the minus 1 over alpha. And this converges as lambda goes to infinity to what's called an alpha stable Levy process. Okay? And this is actually a discontinuous random function. So it's what's sometimes called a jump process, right? And basically, what happens is that when the kernel is heavy-tailed enough, if you look at the largest jump the random walk makes by some time, it's actually of the same order as the total displacement. Okay, so you get this thing where you really see the largest jumps macroscopically in the scaling limit, and that's why you get something discontinuous. Okay. Now, finally, of course, you can ask about, well, what happens when alpha is equal to 2? And in this case, we do still have infinite variance, but only in a very weak way, in that if I look at the second moments, but I introduce some truncation, then it's order log of the truncation scale. So it does have infinite variance, but in this very, very mild way. And what happens is that you actually still get convergence to Brownian motion, but you have to, well, like I said before, if we wanted to always get the standard Brownian motion on the right, I should actually rescale by the variance. You have to do the same thing here, so it still converges to Brownian motion, but you have to put in additional log factor like this. So by the way, this is a very common thing that in these boundary cases, we often get the same scaling limit as in the simple case here being the Brownian case, but with some additional log factors that come in. And although it's kind of a different phenomenon, we'll see that similar things happen at the upper critical dimension in our statistical mechanics models, that you get the same scaling limit as in the high dimensional case, but you have to insert these log factors in order to scale correctly to see the non-trivial limit coming up. Okay. So in particular, if I look at the Green's function, which we'll recall is, well, it's the expected number of times the random walk started at x visits y, which is the same thing as the sum of the transition probabilities. Then this scales like minus d plus 2, the same as we were saying before for the nearest neighbor random walk. When alpha is bigger than 2, it decays like the same power but with a 1 over log factor when alpha is equal to 2, and it scales like the minus d plus alpha when alpha is less than 2. Okay? So in particular, for random walk, this transition between being effectively long range and effectively short range always occurs when alpha is equal to 2. Okay? And what happens is that in the boundary case, when alpha is exactly 2, you are still sort of effectively short range, but you're marginally effectively short range, meaning that, so somehow the convergence to being short range, like to Brownian motion, it's very slow, for one thing. If you do, I'll come back to this in a second, but if you do numerics, it's very hard to see this because the convergence is extremely slow around alpha equals 2, and you get these log corrections coming in. Okay. Good. So what about long-range percolation? So, well, I'll soon get on to this question of when we should expect to be effectively long range or short range for long range percolation. This is very tied up with a really beautiful conjecture or prediction from the physics literature due to a physicist called Sack in the early 70s. I think it's like 73 or something. Okay, now he was working with the Ising model, not with percolation, but again, as with many of these things, or the basic form of these conjectures are exactly the same across all these different models, so let's stick with percolation. So his conjecture, or again, it's a prediction. I mean, he had a not non-rigorous physics calculation supporting this. So let's fix, for now, let's take d strictly larger than 1. And let's try to understand how the 2-point function exponent, so remember this is written here, depends on alpha. Okay? So, the first part of the prediction is that, well, when alpha is large enough, it's unclear how large it has to be, but when it's large enough, the model should it should have be in the same universality class as the nearest neighbor model. And in particular, this exponent should just fixate at whatever it is in the nearest neighbor model, which is something that's difficult to understand. but it's 2 minus eta nearest neighbor, where that just means the corresponding exponent for the nearest neighbor model. Now, on the other hand, if alpha is very small, well, small alpha means large effective dimension, right? Now, we were talking before when the dimension gets large, and similarly here also when the effective dimension gets large, you should have mean field critical behavior, right? Which means that, again, percolation begins to behave the same as branching random walk, okay? But of course, it's not going to be the nearest neighbor branching random walk, it's going to be the branching random walk with this kernel that we were just discussing, this long-range branching random walk, okay? In particular, the two-point function should behave like the Green's function for that long-range branching random walk, which is the same as just the random walk, which is given here. So in particular, for small alpha, you should have this minus d plus alpha scaling of the two-point function, which just means that 2 minus eta is equal to alpha. Okay, so for small values of alpha, we should just see this straight line. This is really the line, just really the line y equals x. Okay. Now, and this should go up until d over 3, which is when the effective dimension is 6. Okay. Now, Sachs' prediction is that if you want to get the whole curve, you just join up these two straight lines continuously. Sorry, that looks like a kink. Let me draw that again. Okay. Now, you know, I'm not, of course, giving you the reasons why he predicted this. It wasn't just that he connected up these two lines, but that is indeed what the prediction is. Okay. And so in particular, you get, according to this prediction, you get this value alpha c, which is called the crossover value, which is where you transition between the effectively long-range and effectively short-range behavior. And you know, alpha c should be given by 2 minus the nearest neighbor value of eta, both of which depend on the dimension. Okay. Good. So this conjecture has been at least somewhat controversial in the physics literature. So as a brief history, there was an earlier paper a few years before Sachs by, I think by Fisher and some others, and they had a more complicated prediction for what this curve looks like. It wasn't just this straight line. And these computations are based on a renormalization group analysis. And what Sachs showed is that you have to somehow do all your analysis to infinite order to get the correct answer coming out. And he showed that it should just be this straight line.
Much more computation to predict something much simpler.
Yeah, I guess so, yeah. Right. Yeah, and you know, one thing that's worth pointing out is that when the physicists do these things, you know, the way they're doing them often is via these expansions, right? Where you expand around alpha being slightly larger than d over 3. And even when they have a prediction like this, they'll sometimes be careful to say, this prediction holds to infinite order in the perturbation theory, but you know, maybe the function is not actually described exactly by its expansion. I mean, we know that can happen, right, in general for functions. And so sometimes they don't really claim that this is the graph, they just claim that, you know, like all the derivatives vanish at this point. Or not vanish, but you know, if you cancel off the linear term.
Yeah. Is the exponent the same as predicting that the largest edge has the same size as the cluster? That in the scaling limit?
No, I think actually that what happens is actually the longest edge is sort of, this sounds silly, but it has much larger diameter than the cluster, in that if you look at a cluster, it will have these very long hairs coming off of it that are actually invisible in the scaling limit because they have no mass. That's a good point, because when we were discussing hyperscaling relations before, I was often saying, okay, you can compare this two-point function to these two one-arm events or something like that. You really don't want to use these one-arm events for long-range models because they behave very poorly. They're dominated by these rare long edges that you should really ignore in some sense. So yeah, you are on the right track though, and I'll come back to saying the more accurate version of what you're asking later. Okay, good. So yeah, so more recently, maybe 10, 15 years ago now, there was, for example, a paper in the physics literature where they said, okay, let's just compute these things numerically. This is for the Ising model, but again, you shouldn't really expect things to be too different. And if you do this numerically, you really don't see this corner. You see, this looks good, it looks like a line, and then you have some very smooth transition between the two things. And they said, okay, well, maybe it really is true that, these things hold to infinite order, maybe all the derivatives coincide, but, it's actually just not the same function as you go away from d over 3. But in fact, there's a good way of discounting this kind of argument, which is that you can do exactly the same numerical simulations for simple random walk, and you see exactly the same thing. It looks like you run the random walk for whatever millions of steps that you can get to run on your laptop, and you see exactly this picture with a very smooth transition between the two things. But of course, for random walk, I didn't prove this to you, but it's very classical and not very hard to prove that you do in fact have this corner in the limit. Okay, and the issue is just that numerically, whenever you should see log corrections appearing, you should think that means very slow convergence is occurring. Okay, and in particular at this corner, if you do a finite dimensional system and you do a simulation, you compute the exponents numerically, you're going to get very, very slow convergence to the true exponent at this corner, but of course also near the corner as well. Okay, and that's why you see this smooth thing, and it's not really, I think it seems pretty clear in the example of random walks that this is just methodologically not a good way to go.
But you shouldn't see the smoothing part on the alpha larger than alpha c. You stay straight until alpha c and then be smooth.
I think even if alpha is, for the random walk, if alpha is like 2.001 or something.
You don't feel the log, right? You still.
Yeah, I'm not completely sure. Maybe you may.
It's central in the curve. You don't have a log.
Yeah, but the constants for the second order term in the CLT can be very large. Right, you only get the log at exactly that point, but of course, the fact that you have the log exactly at that point means some constants are degenerating near the point, and you'll still have, the slow convergence is, the numerical things don't know that you're exactly at alpha c, right, or not. Okay. Good. So, by the way, this is the picture for d bigger than 1, but if d is equal to 1, then the corresponding conjecture is just that you only see this straight line. You never transition to the nearest neighbor type behavior because there sort of is no nearest neighbor critical behavior. And this goes from 0 to 1. And here this is 1 as well. And of course, this corresponds to minus d plus 2 minus eta being 0 at 1, which means you have non-decay of the two-point function. Of course, as I mentioned, actually, if you take the model with d equals alpha equals 1, you actually get a discontinuous phase transition. So it's consistent with this conjecture. Okay. So, one of the most interesting things about this prediction is that, I've told you that you should expect a lot of behaviors to change as you cross this threshold d over 3 when the effective dimension becomes 6. Okay, but of course you don't see this at all in this picture, right? It's just a straight line. It just goes straight through this. Nothing changes. But you should see the change if you look at other exponents. So, for example, if you look at delta, which is the volume tail exponent, and let's again take d at least 2. Let's say d between 2 and 6, actually. Then you will see something happen here. Okay, so for alpha up to d over 3, well, the model will be mean field. You'll get delta equals 2, right? That's the mean field value of this exponent. It corresponds to percolation behaving like a branching random walk.
I'm sorry, that's the tail of what? What is K?
Oh, sorry, k is the cluster at the origin. Yep, and absolute value k means the number of vertices. Okay, so up to d over 3, this should just be 2. And of course, similarly, once I reach alpha c, which has this complicated value, the delta should fixate at whatever its nearest neighbor value is. Okay, what about in between? Well, here it should be d plus alpha over d minus alpha. Okay, now this particular conjecture, it actually just follows from this conjecture plus the hyperscaling relations that we were talking about last time. So let me explain that in a bit more detail. Okay, so in fact, this is another one of these hyperscaling arguments. It's actually not one of the ones I told you last time. So remember, we were talking about how if you look at all the clusters in a large box, then you should imagine in low effective dimension, there's basically order 1 important clusters in this box that determine everything. Whereas in high effective dimension, you have some kind of soup of many large clusters that you need to consider all of to understand what's going on. Okay, so in low effective dimension, let's say the largest cluster in the box of radius r has size r to some exponent, df, for the meaning the fractal dimension. Okay, and we saw last time that in low effective dimensions, what you should expect, again, like from heuristic arguments, is that for in low dimensions, you have the hyperscaling relation 2 minus eta is equal to twice the fractal dimension minus the ambient dimension. Okay? Or, yeah, okay. So how can we relate this to delta? Well, the idea is that let's suppose we want to look at the probability that our cluster is large. Okay? Now again, this is going to be just a heuristic argument, is not a proof in any way. We should say, what we want to say is that the best way to be in a large cluster is just to be in the characteristic large cluster at some scale. Okay? So what we do is we set m equals r to the df. So we set, in other words, take r is m to the 1 over df. Okay? And what we expect is that this probability is of the same order as the probability that the origin is in the large cluster at scale r. Okay? And again, we think of in low dimensions, there are order 1 such clusters. So this probability is just the size of that cluster divided by the total size of the box, roughly. Okay? So, if you then, do the inversion, so you want to write this back in terms of m, what you get is that delta is equal to df over d minus df. Okay? And if you take these two relations and you do some algebraic manipulation, what you get is that delta is d plus 2 minus eta over d minus 2 plus eta. Okay? Which, of course, in this regime, 2 minus eta is alpha, right? So that exactly gives us this d plus alpha over d minus alpha, assuming the validity of the other conjecture and that these hyperscaling relations hold. Okay? By the way, it's also convenient to, let me just write down, with any of these relations, you can solve for one or the other of the parameters, and it's useful to write both of them down. So the other way of writing it is that 2 minus eta is equal to delta minus 1 over delta plus 1 times d. Okay, so these are just the same relation written in two different ways. And again, these are things that we only expect to be true below the critical dimension, or also at the critical dimension, in which case, these arguments may not capture the correct powers of log, but they should give the right exponents. Okay. Okay. So in particular, even though we don't see anything interesting happening at d over 3 in this picture, we do expect to see something interesting happening for other exponents like delta. Okay. And another thing to point out is, the really nice feature of this conjecture is it's telling you that you have these models which are really they're not mean field and they're not planar, you don't have all the special stuff that you have in 2D. So they're really these models of intermediate dimension, but they have at least some exponents which have nice values. Okay, and that of course puts you in a much better position to at least hope to prove theorems, right? When you have some exponents that you might be able to compute exactly. On the other hand, if you look at some other exponents, for example, gamma, which is the susceptibility exponent, nu, which is the correlation length exponents, beta, which is this exponent for the density of the infinite cluster above beta c, and I apologize that beta appears in both places, but that's just how it is. None of these exponents are believed to have a simple exact formula in this intermediate regime. Okay, so this is not something that we have done yet, although I think it's something we're on the precipice of being able to do. But if you want to study these things, maybe you have to start doing these expansions.
Yeah, I'm sorry, I missed
Yeah.
the beginning of this. So I don't know what these exponents are. But
Oh yeah, they're all written here actually, apart from eta, which is the, I'll write that one too.
No, don't worry.
Yeah. I think this won't come up that much actually. Where this is the correlation.
There are other exponents that I like very much.
Mm-hmm.
We now understand the dynamics of the random walk on the critical thing when you are in the easy regime.
Yeah.
The in field.
Yes.
We've been working 10 years.
Yeah.
But indeed, and of course, the critical dimension we can do it is not 6, it's like whatever, 9 or 10,
Yeah.
just because we're lazy. But in this model, the long range, where you have this intermediate thing, is there any prediction of what the
No.
limiting dynamics would be of the random walk?
No, I mean, well, the first more basic question would be to understand what do the clusters look like as metric spaces, right?
Yes.
And that we also don't know. One thing I would say is that in ongoing work, which is less complete than the other ongoing work I'm telling you about, with my postdoc Lily Reeves, we're all those things you were just talking about the metric properties of the clusters and the random walk properties. We think we can understand certainly above the upper critical dimension, but we think we can also probably prove everything at the critical dimension as well, and getting all these log powers. And one thing I'd say is some of these log powers are quite complicated, which suggests that the exponents, the expansion is also going to be, because one of the general phenomena that I was talking about last time is that the powers of log at the critical dimension should encode the derivative of the exponents as you go below the critical dimension. And so, for example, I should say these things are subject to revision because it's very hard to check these numbers are correct. But the power of the logarithmic correction for the effective resistance on the clusters appears to be 5/24, for example. So whatever your exact function is, like its derivative is going to be 5/24. And again, the chemical distance, the exponent's 3/16. Although a few weeks ago, I was telling people it was 19/192, but there was a mistake in that computation. Again, it's difficult to know that you've done it correctly because, what do these things mean? But in any case, it certainly seems like you'll get some fairly complicated values for these log corrections, and therefore that even more strongly suggests complicated behavior in the low-dimensional regime. Okay. Good. So one way we can sort of summarize this picture of what's going on is that is to do a sort of phase diagram of the different regimes of the different critical behaviors the model can have as we vary d and alpha. And what happens is there are these 4 different regimes. So this is the line d alpha equals d over 3. This is 6. By the way, this looks a bit like a 3-dimensional picture because you have these 3 lines meeting like this, but it's just a 2-dimensional picture. It just looks like that. This is 2. This is the line alpha equals alpha c, which is something complicated. Okay? And these different regimes, well, you have 2 different switches that you can flip kind of independently of each other in some sense, which is the model mean field or not? And is it really long range or not? Okay? So what we expect is that we have this regime where you are long range and high dimensional. This regime where you are effectively short range and high dimensional. This regime where you're short range and low dimensional. And this regime where you're long range, low dimensional. Okay? So in particular, your critical dimensional along these 2 lines, which is these 2 lines together are where the effective dimension is 6, and your marginally short range along this curve here, which includes these 2 pieces. Okay? So in particular, and of course this is something you also see here, right? In high dimensions, the nearest neighbor value of eta is just 0, so we get alpha c is 2 in high dimensions. Whereas in low dimensions, well, one thing I should stress about this picture is that, I've drawn it down to 0, but of course d is really an integer, and the interpolation of this picture down to 0 is highly non-unique, so don't, draw too much from it. Okay? But alpha c of 1 will be 1. Alpha c of 2, well, it's 2 minus the nearest neighbor value of eta, which is 5 over 24, so it's 43 over 48. And then, alpha c of d for is 2 for d larger than 6. And, for the intermediate dimensions, we only have some non-rigorous epsilon expansion things and also just numerical estimates. So the values I'm about to write out, they're just, there's a Wikipedia page called Percolation Critical Exponents, which is very good, actually. It has big tables of all these different things, all the different numerical estimates and exact values and so on. And I'm just going to write down the intervals of the different reported values for this exponent, which you can find on Wikipedia. So I'm not claiming that all of these are equally likely to be true. In some of these papers, in particular, this includes things from very old numerical papers, and I'm sure you could get much more accurate estimates now. But alpha c of 3 is somewhere between 2.03 and 2.08. Alpha c of 4 is between 2.08 and 2.13. And alpha c of 5 is between 2.05 and 2.08. In particular, if you believe these numerical estimates, and again, I should say some of the values in these ranges are numerical. Some of them come from the non-rigorous epsilon expansion method. It does appear that you have this non-monotonicity like this. Okay, so in particular, alpha c of 2 is less than 2, and alpha c of d is bigger than 2 for d between 3 and 4. And of course, if we also have this epsilon expansion, which is that alpha c of 6 minus epsilon should be 2 plus epsilon over 21 plus dot, dot, dot. Okay. So again, none of these things are known rigorously except the one-dimensional case and the high-dimensional case.
Two-dimensional case is not known rigorously?
No. Yeah, the thing is, like in 2 dimensions, there's really, as it stands, one model where we can analyze the exponents, and it's site percolation on the triangular lattice. Yeah. In order to prove this, you would need some very, very strong version of universality, right? That would say even not just for nearest neighbor models, but for long-range models with sufficiently fast decaying kernels. And even then, you have to get it all the way down to this critical value where it ceases to be the same universality class, right? So, I think, one thing about this is that, of course, this boundary between the short-range low-dimensional and long-range low-dimensional is going to be extremely difficult to understand. Okay, so I think, the approach that I've taken for this regime is to say, okay, well, let's just try to define axiomatically what it means to be in one of these regimes in some kind of weak sense, and then try to compute the exponents, prove all the things we would conjecturally like to be true, subject to that assumption. Okay?
But this value of alpha c of 2 is predicted through some conformal invariance, aren't you?
Yeah, I mean, alpha c is 2 minus eta nearest neighbor, right? So, yeah. So I should say, yeah, it's really that the relation between alpha c and eta nearest neighbor just comes from the SAC prediction, and then eta nearest neighbor comes from the conformal invariance. I guess it was originally done through the Coulomb-Gass methods by Nienhuis. Okay. Yes. Actually, maybe that's a good time to mention a brief aside, which is which I should have said last time. So that this take yourself back to being in Friday's talk. I talked a bunch about how in physics, one of the main ways they understand models in intermediate dimensions is via the epsilon expansion. But in fact, this was the main way of doing it for a long time, but now for the 3D Ising model in particular, and many other models, they have a much better way of understanding the exponents in 3 dimensions via something called the conformal bootstrap. So I won't say very much about that, but I wanted to say a little bit about conformal invariance now to introduce some foreshadowing for later in the talk. So the idea is that in 2D, well, for the nearest neighbor model, as you mentioned, a really central idea is that you get conformally invariant scaling limits. Right, so this means, a conformal map is a map that preserves angles, right? So in 2D, this is really powerful because you have tons of conformal maps by the Riemann mapping theorem, right? You can map conformally any simply connected domain that's not the whole plane to any other simply connected domain that's not the whole plane. Okay? And this is really underlying a lot of the progress that has been made in 2 dimensions. Okay? But in fact, it's believed that this is actually true in any dimension. Maybe I should say bigger than 1. You have arguably in 1 dimension, like any monotone function is a conformal map. It certainly preserves angles, so let's ignore that. But there is a version of this that's correct in 1 dimension too, which is that once you get to dimension at least 3, you no longer have the Riemann mapping theorem, right? It's not true that you can generally identify different simply connected domains with each other. In fact, Liouville's theorem says that the only conformal maps you have, even defined on just open sets, are Mobius transformations. Okay? And what does a Mobius transformation mean in d dimensions? Well, they're just the functions that the group of transformations generated by all the Euclidean transformations, so isometries plus dilation, plus inversion in the unit sphere. Okay, in other words, plus the map x goes to x over absolute value x. Maybe I'm supposed to include a minus there to make it orientation preserving, but in any case, you also have invariance under the anti-Mobius transformation, so let's not worry about it too much. Okay. Yes. Thanks. Okay. You have way fewer Mobius transformations than you have conformal maps. But what physicists have found is that in 3 dimensions, for example, the fact that you also have this additional symmetry in the scaling limit beyond the Euclidean ones, like the scaling, translation, rotation, etc., actually places a lot of constraints on the model. And in particular, they're able, for the 3-dimensional Ising model, to determine in a sort of semi-rigorous way, I can say more about that offline, they can determine the exponents to 10 decimal places, okay, which is, of course, more than sufficient for any real-world, an experiment or simulations or whatever. Okay, and so I think this is something really interesting that I'd say, like, our community of people doing mathematical physics within probability really, as far as I know, has not begun to grapple at all with this issue of Mobius invariance outside of 2 dimensions. So although I'm not really going to do that, there will be some things that come up which at least gesture towards starting to understand that in this context of long-range percolation, which I think is really interesting. And by the way, I should say that these kind of Mobius invariant things, they do also work for long-range models. So even in 2 dimensions, if you look at long-range model, like you, for example, just think about Levy processes, they actually will be Mobius invariant, even though I would imagine that the Levy processes in 2 dimensions will not be invariant under the full group of conformal transformations, although I haven't checked that. I would be surprised if it was true. Okay, good, but that's just an aside. Let's see how I'm doing for time. Maybe it's a good time to take a 5-minute break. I imagine many of you are looking forward to actually seeing some rigor in this course. I've been talking a lot about heuristics and these physics-style arguments and so on, so I want to actually, we have seen a few proofs actually, but now I want to really get onto the math portion where we start proving theorems. So my plan is to first, in the remainder of today, give an overview of all the results, everything we know, the rigorous versions of this whole story that I've just been explaining. And then I'm going to be proving many of these theorems to you, or at least sketching some of them over the rest of the week. Okay, so let me start by saying in the case that the effective dimension is 6, it's strictly larger than 6, then you're in this regime where you have high effective dimension and you can do a lace expansion analysis. Okay, and again, I didn't really go into any details at all about the lace expansion, but it's a way of proving mean field critical behavior for high dimensional models, again, that was introduced by Bridges and Spencer, and then heavily developed and applied to many more models in the work of Harenside. Okay, and in the particular case of long-range models, this was done by Heidenreich, van der Hofstad.
The usual suspects.
Yeah, well, there are some other usual suspects that are not on this list. In particular, Harenside are not on here themselves. Van der Hofstad and Sakai, and by Chan and Sakai. Okay, in particular, there are several works of Chan and Sakai on this. And one thing I'll mention specifically about this work of Chan and Sakai, or at least one of their papers, also does this boundary case D equals 6, alpha equals 2. Okay, and the interesting thing is that this is this point right in the middle here where all of these curves meet, and you might think, well, something really interesting must happen at that point, but actually that's not really the case in some sense. It turns out that this point essentially belongs to this line, alpha equals 2, in that it's just mean field. There are no logarithmic corrections to mean field, if you like. There are logarithmic corrections that come from being on the line alpha equals 2, which are a sort of a different form, right? So, you get in all of these cases that the critical 2-point function behaves like this Green's function that I wrote above, right? Maybe I won't write that down again because it's just there, but in particular, you get the minus d plus 2 when alpha is bigger than 2. You get that divided by log, in this case alpha equals 2, and you get the minus d plus alpha when alpha is smaller than 2. In particular, that log is actually enough to make the triangle sum converge in this marginal case d equals 6. And so the fact that you have the log there, which is not a logarithmic correction to mean field scaling because it's just there in the random walk, which is like the non-interacting thing that you want to compare to. It's a different kind of log correction that comes from being marginally short range. This actually makes you already exactly mean field. And so you can treat this. It's more delicate, as you can imagine.
So usually in this expansion, they need df much larger than 6. Why?
Yes. So, well, I'd say actually that the thing with the Leçons expansion is you need a small parameter, but that doesn't have to be how you get it. So, but of course, these Leçons expansion methods, they do have this usual caveat that you need to work with spread out models. Which in the context of long range models means that J is constant on a large ball. Okay, so you get this up to some large constant scale, you look like you're doing percolation on the complete graph, and then it starts to decay. Okay, that's like the analog of working with these spread out models for short range models. Okay, so in particular, this is what we sometimes call a perturbative approach to the critical behavior, in that you need some you need to start off close to the mean field model. With these spread out models, it's like, again, up to some large constant scale, you behave exactly like you're doing the Oda-Shreni random graph, percolation on the complete graph, and then you start to fill the geometry.
Okay. So this result is valid for that, right? For this,
Right. All of these results hold for spread out.
D is much larger than 6. Can you just get rid of it? Or?
Yeah, I mean, you have to. It depends what your kernel is, right? Depending on the thing is, it's like if the Fourier transform of the kernel has some LP estimates or something. That's like the true assumption here, and you can achieve that in various ways.
So the least expansion analysis is a perturbation model?
Yeah, it's essentially what the Leçons expansion is you can imagine that you one way you can understand this 2-point function. you might want to, this is maybe an overly caricatured description, but you might start by saying, okay, this 2-point function is kind of like just counting the expected number of open paths between these 2 points. But then, okay, that's not true because of course you can have more than one open path. And you try to do like an inclusion-exclusion expansion. And just doing it the way I described is terrible. I mean, you shouldn't do it that way. The Lace expansion is like the correct way of doing that kind of analysis so that you can sum over sort of corrections to the geometry, you know, the fact that basically the paths in the clusters are non-unique, kind of summing over with some alternating sum for fixing the fact that you overcounted and then undercounted and overcounted again, so similar to inclusion-exclusion. So I won't say more about that, but the issue is basically that you get these expansions for the 2-point function, and you need to show that these expansions converge. And basically, in order for them to converge, you need some parameter to be small. Okay, where the parameter are really some complicated things associated to the kernel, but you can imagine once you get to high enough dimension for the nearest neighbor model, or once you work with a very spread out model, that makes this parameter small and it makes these expansions converge. And it's actually unclear whether they do converge, I would say, for just under this assumption, for example.
It's a little puzzled because long range is already spread out in some sense because you.
Yeah, well, yeah. That's why they're different, though. I mean, again, you should think the real condition is that you have some quantity associated to the kernel that has to be small. You can, this is not really how it works, but you can imagine you compute the triangle diagram for the random walk Green's function, and you need this open triangle diagram, and you need it to be very small. One way of getting that is to use a spread out model. But you know, it's not. For just an arbitrary long-range model, it's not necessarily the case that that triangle diagram is small. Okay. But you know, these are the limitations of the method, and you know, one of the things I want to tell you about is this new work removing these kind of assumptions, but it's via a different method. Okay. Good. Okay. So that's sort of where things stood, and I mentioned before as well the work of Berger, which proved that if just under the assumption that alpha is smaller than d, that the phase transition is continuous. And by the way, if you draw that line on this graph, well, it looks again you have to be careful because this part of the graph is not uniquely defined, but it's something like this, right? In fact, it may even be significantly steeper than that line I've just drawn. So, in particular, this region alpha less than d that Berger's result treats certainly does cover models that are effectively short range. Okay. On the other hand, Berger's result is just qualitative. It doesn't tell you anything about exponents. And the reason why there are kind of two main ways that you can try to understand, or let's say to prove that there are no percolation clusters at criticality. You can either start by just trying to prove exponent estimates and so on, and understand things quantitatively. And the way you typically do that, I mean, there are many variations on this, but you tend to approach the model through the subcritical regime somehow and try to prove uniform estimates so that remain true as you approach the critical point. And that's something we'll talk a lot more about over this week, and that's in particular the Lace expansion could be thought of as a method in that vein. So this is sometimes what I'll call the subcritical strategy, right? On the other hand, there's the supercritical strategy, which is to try to say, suppose you're at some value of p or beta, and suppose you know that there are infinite clusters exist, almost surely, then try to prove that you're strictly above the critical point, i.e. that if you reduce p a bit, you'll still have an infinite cluster. Okay? And this kind of method, it tends to work via much more sort of ergodic, theoretic type techniques. It tends not to be quantitative, or sometimes if you work hard, you can extract some quantitative information from these kind of proofs, but it's often extremely weak. And Berger's proof is more in this vein. It's a supercritical strategy. He says, suppose you're looking at long-range percolation and you have an infinite cluster, then in fact you'll still have an infinite cluster if you reduce beta a bit. Okay, so it doesn't tell you anything about the critical exponents. So my first work on this model, which was 5 years ago now, said that you can at least get some power law bounds on these quantities. But with the wrong exponents. Sorry. And the 2-point function, if you sum over a box, is also decaying like a power. Again, with both of these being the wrong power. Okay?
I'm sorry, I can't really read from here. The power you would expect would be d plus alpha over d minus alpha. And
It's actually d minus alpha over d plus alpha. Delta is 1 over the power here. And here it should be minus d plus alpha. So these are just, they're not the correct exponents. I just wanted to mention this as a historical step on the road to the stronger theorems that we're going to state soon. Okay, and this is again for alpha smaller than d. In fact, this is also true for alpha greater than or equal to d, but it's vacuous. I mean, like, this would say that this bounds it by something growing, and similarly for this 2-point function. Okay, so in some ways this result is obsolete now, although the proof of this introduced some interesting methods that are still going to be very important, which I'll tell you about later. Including, in particular, one of the key steps here is rigorous hyperscaling inequalities, and in particular, an inequality form of this. Just make sure I write down the inequality the right way around, sorry. Yes. Which is 2 minus eta bounded above by delta minus 1 over delta plus 1 times d. Okay, so we'll see. I'll prove this to you later. So, this is going to be a concrete inequality that relates these spatially averaged 2-point functions to the volume tail. And in particular, if you assume that both of these exponents are well defined, then it gives you this inequality. And this holds, for percolation in any dimension, nearest neighbor or short range, whatever. Okay, and both this inequality and its proof are going to be very important in the future, in the further developments. Okay, and again, this is an inequality, but this should be an equality below the critical dimension, but not above the critical dimension. Okay. So this was, my first entry into this subject, and, in fact, when I wrote this paper, essentially I had a method that I just wanted to find nice applications for. I guess that's often what mathematicians do, right? You have a hammer and you go around in search of nails. So in fact, the method that I used for this paper, it actually came out of work with Jonathan Herman about understanding percolation on groups of intermediate volume growth. And I I had this idea that, this method should actually work for long-range models on ZD, maybe with some extremely, ridiculously slowly decaying kernels. And I thought, okay, at some point when I'm bored, I'll figure out what it tells you. And I kind of assumed, because in the original context, it worked for these big groups that are very, very far away from being ZD. So I assumed you'd need some quite outlandish assumptions on the kernel. But when I eventually spent the time to do it, I realized actually it just needs, after some optimization, just needs alpha less than D, which is like a pretty good condition, actually. I mean, it's, and in fact, I actually didn't know about Noem's proof of continuity under the same assumption, so I was even more excited about this than I had the right to be, perhaps. And I decided then, I need to write the introduction to this paper, right? So I need to figure out, how this fits into what's conjectured and what's known. It was only then that I learned about all these beautiful conjectures of SAC and so on. And this is really when I got hooked on this problem, and I was like, okay, come on, there's such a nice conjecture about what the 2-point function is. Surely we can prove this. Okay, so with a view to trying to actually be able to compute exactly the exponents, I decided to work first on the hierarchical model, and this is something that we'll use later on as well. So I want to introduce it now. Okay, so the d-dimensional hierarchical lattice is going to have this parameter L, which is sort of the arity of the hierarchical lattice, if you want. So how is this defined? It's going to be ZD, but with a different metric. Okay, which the way you can think about it, you take an L-adic decomposition. So let me just explain what that means in pictures. So e.g. D equals L equals 2. L has to be at least 2. You say you take all your lattice points. Okay, and then you first partition them into 2x2 boxes. And then into 4x4 boxes in a consistent way, and then into 8x8 boxes in a consistent way, and so on. And one thing you'll notice here, this choice of decomposition is not unique. And in fact, later on, we'll actually want to consider the space of all possible such decompositions and do some compactness arguments within this space. But for now, for defining the metric space, it doesn't matter which one you take, as long as you don't always pick the same direction, otherwise you'll get you'll get points at infinite distance. So do this with some generic choices. And so we'll define the metric to be the side length of the smallest box we'll often call this a block. So this means the distinguished boxes in the decomposition containing both points. Okay, so in particular, these 2 points have distance 2. These 2 points have distance 4, even though they're in the same piece. And points here will have distance 8, even though they're next to each other in the Euclidean geometry. Okay. So this has the property that for a sort of generic pair of points, the distance will be of the same order as the Euclidean distance. But on the other hand, for some pairs of points, the distance is much larger than the Euclidean distance. Okay. Good. Okay. So, the first theorem actually establishing a real exponent beyond the mean field setting was for the hierarchical model. So, of course, for long-range percolation, we're just going to define it exactly the same as before, right? We have a kernel, we have an edge between 2 points with probability 1 minus eta minus beta times the kernel, except now we're going to take J to be, and of course, this hierarchical metric is of course not translation invariant at all, so it makes sense to use this 2-parameter version of the kernel. And we'll set this to be, I'm going to write the, actually let me use this hierarchical, I'll write it like a norm. Of course it's not a norm, it doesn't really depend on the difference between x and y, but just to make the notation look similar to the Euclidean case. Okay. So this is hierarchical. And as before, we'll take this kernel. And the theorem is that the critical 2-point function is up to constants the same as the distance, and here we take alpha less than d. Okay. In fact, for the hierarchical model, if alpha is bigger than or equal to d, there is no phase transition. Okay. One remark about this, by the way, is that the model only really depends on the ratio. So, the dimension is kind of a fake parameter in these hierarchical models. But this is because if you take this L-adic d-dimensional hierarchical lattice, this is equivalent in some sense to the one-dimensional one, which is L to the d-adic, by a map that distorts distances by a power. So it's not exactly an isometry, but if you have the metric here and the metric here, they're the same, except you have to take a power at the metric, and that just transforms this kernel into the -1 minus alpha over d kernel.
If you had done something simpler than this hierarchy, if you had started from a tree, let's say, large tree, and do this long range thing on it, would you get that easily?
Yeah, so you can equivalently think of this as being a model defined on a tree, except it's on the leaves of the tree, right? So it's like you so this is particularly clear in one dimension, right? You have like this sort of infinite binary tree with leaves, what we call the canopy tree. But then the model is like defining random long edges on the leaves, right? So if you say percolation on the tree, it sounds like you're doing something trivial. But here it's actually in many ways very similar to long-range percolation on ZD. You just change the metric. It's not like the paths in the clusters are paths in the tree at all.
Would it be simpler if you started directly on the model like?
It's exactly equivalent. It's exactly the same. Yeah, so in this tree representation, the distances on the leaves are defined to be like 2 to the height of the nearest common ancestor. Okay. One thing I'd say about this, by the way, I don't think it is the right thing to think about this as a model on the tree, really. And in fact, the situation is exactly analogous to, you can think of RD, of Euclidean space, being the boundary of hyperbolic space of the same dimension, right? So the hierarchical models you can think of as being models on the p-adics instead of RD. And the relationship between the tree and the p-adics is exactly the same as the relationship between RD and hyperbolic space. So, I don't think you should think of this model as being a model on the tree any more than you think of percolation on RD being a model on hyperbolic space. It's like, that perspective might be interesting for some things, and indeed, like within physics, there's this whole theory of the ADS-CFT correspondence, right, where maybe here we have a conformal field theory on the boundary, so maybe it corresponds to some quantum gravity model on the tree, although I don't expect that to be the case for percolation on the boundary. Or at least I don't know of any reason why there should be a connection to quantum gravity, but that's more like how the analogy works. It's not really that you're doing a model like on the tree per se. Yeah.
And can this hierarchical model help in the conformally invariant scaling limit?
Yeah, so that's an interesting question. I mean, generally speaking, the hierarchical models are easier to understand than the Euclidean models, and you can still expect to have Mobius. There is a notion of Mobius transformations on the p-adics, and one could try to take scaling limits of the hierarchical model, and these may be easier to understand. And in fact, this has actually been done not for percolation, but for some spin systems like the phi-4 model, I guess, in the work of Abdelmalek Abdesalam. So he showed you can actually, including in the intermediate dimensional regime, for the hierarchical models, you can basically implement this whole epsilon expansion stuff, but in a way that actually gives you a scaling limit, which is some small perturbation of the mean field scaling limit, and which he shows is actually Mobius invariant. So yeah, it's something you can study on the hierarchical case, and it may be significantly easier than the Euclidean case. For percolation now, the status is that we understand, as I'll say soon, both models about equally well actually, and but of course for further investigation it might be better to do hierarchical first. I realize I'm nearly out of time for today, so maybe I'll just I'll finish by just saying what the status of these things about the two-point function are for long-range percolation on ZD. And so one way one further point I want to make about this hierarchical thing. So, the SAC prediction is that the two-point function depends on alpha like this, and so you get these two different regimes. And the way you can think about this, in light of this result in particular, is that for alpha bigger than alpha c, the model is behaving like the nearest neighbor Euclidean model, and for alpha less than alpha c, it's behaving like the hierarchical model, right? And one way you can think about how that works is that, when I have two large boxes and I put them next to each other, and I have my large critical clusters here and my large critical clusters here, you can think, how are these clusters merging together as I go to the next scale to form the big critical clusters on the next scale? Okay, and there are kind of two natural kind of strategies vaguely defined that they might take. One would be that, these clusters, they're kind of like equidistributed in space, and they mostly just say, oh, well, you just take these bulk edges, right? You just find these long edges that happen to connect one cluster directly to another, and that's sort of a bulk-to-bulk connection. Another way is that maybe these clusters, they go near the boundary a lot, and they tend to just find each other on the boundary and get connected by short edges, okay? Which is sort of a boundary-to-boundary interaction. So one way, heuristically, you can interpret this conjecture is that there's these two phases. When alpha is large, the boundary-to-boundary interaction dominates, and the model begins to behave the same as the nearest neighbor model, which you can think only has boundary-to-boundary interactions, right? There are no bulk edges. On the other hand, when alpha is smaller than alpha c, the bulk-to-bulk interactions dominate, and the model begins to behave the same as the hierarchical model, which you can think only has bulk-to-bulk interactions, right? Because in this, when I take a hierarchical box here, right, there's no special relationship between the points that happen to be next to each other in the Euclidean embedding, right? In fact, any point in this 8x8 box has the same distance to any point in this 8x8 box next to it, right? The geometry doesn't matter, okay? So again, it's reasonable that just one of these strategies will dominate, except possibly at this point alpha c, where you can imagine maybe they're comparable and then you get some logarithmic corrections and complicated things going on. But otherwise, probably one or the other of these strategies dominates, and then you should behave the same as the model that only has that interaction. Okay, which you can think of as a heuristic argument for having this change in behavior. Although it's not the one that Zach gave. Okay. Maybe it's actually a good time to stop for today, and then I'll tell you about the more results on the Euclidean model next time.
Any question? Gérard?
So, do we understand the notion of incipient infinite cluster in this kind of case?
Yeah.
Since we know that it doesn't exist, but the infinite one, but...
Yeah, so actually it's an interesting thing where I can prove various results about that, which I've been debating whether to include in my paper or not. It's already very long. I can tell you basically, well, for one thing, in the regimes where we can understand things through the Lace expansion, I'm not totally sure, but I assume you can construct the IC in the usual way using the Lace expansion. In fact, my new methods show that the ISC is well defined both in the high dimensional regime and on this critical line here. And in this regime, the long-range low-dimensional regime, they show that it's well defined up to constants in this very frustrating way that sounds like it should imply. Basically, I can show that any two subsequential limits are absolutely continuous with respect to each other with bounded derivative. And it's very, very close from there to say, okay, the limit should surely be well defined, but I don't have an argument yet.
Other question? Nikuna?
So in the critical case,
Yeah.
same question, do you see then critical case, so when the boundary effect
Alpha equals alpha c, you mean?
there in the two-point function, when the boundary effect are the same as the bulk,
Yeah.
do you see long edges in the scaling limit? Or do you expect?
No. I can, but you see marginally long. Not that we can prove things about that exactly, but what I expect to happen. So, okay, the correct way to understand this long edge thing is if you condition on two faraway points being connected, does the path between them include edges, macroscopic edges? Okay, that's better than, you don't want to look at the longest edge in the cluster because that's much longer and it's not really important. And what I believe will happen, and I can tell you more about my evidence for this, is that at this alpha c, the longest edge in the path between x and y will be smaller than the distance between x and y by a polylog. So in particular, actually, if you did a simulation, it would look like you had macroscopic edges. But they'll actually be just barely, and it's related, it's similar to how in the Brownian motion, in the random walk, right? It still converges to Brownian motion, but like the largest jump is only smaller than the total displacement by a log factor, polylog factor.
How can we analyze the convergence between the two boundaries in the second case?
Yeah, well, I guess what I'd say is that I'm not going to say very much about that regime. Well, that's not quite true because I will show you a bunch about this short-range high-dimensional regime, but the analysis doesn't go through any kind of analysis of this picture. I think that's a very difficult way of approaching the problem, but it's heuristically what you should think of as going on.
And have you a paper about it, just out of curiosity?
About this particular thing, no. There are papers about some related things in high dimensions, like in particular what the intersection of a cluster with the boundary of a box looks like in high dimensions. For example, by Hansen, Chatterjee, and Soso. But yeah, this is more like as a guiding heuristic rather than how we'll actually analyze things. Okay, let us thank Dom again. Thank you so much.